All right, let's talk about some invisible forces. Forces that are acting on you right now, but you probably don't even think about them. We're talking about the normal force and tension. They're basically the hidden scaffolding that holds our physical world together, and today we're going to pull back the curtain and see exactly how they work. So let's just dive right in.
So, here's the game plan. First, we'll tackle the force that's stopping you from falling through the floor. Then, we're going to take that idea and hit the slopes, a ski slope to be exact, to see how things change when you're on an angle. After that, we'll deconstruct gravity itself, which is super cool, and then we'll switch gears completely to the force of tension and wrap it all up with an example that is seriously going to blow your mind. Trust me.
Okay, first up, let's get into that unseen support force. You know, the one holding you up as we speak.
So, have you ever actually stopped to think about this? Why aren't you falling through the floor right now? Gravity is relentless, right? It's always pulling you down. So what gives? What's stopping you? Well, it turns out there's this quiet but incredibly powerful force pushing right back at you.
And that pushback, that's what we call the normal force. Now, I know what you're thinking. Normal? It sounds kind of boring, right? But in physics, normal has a super specific meaning. It means perpendicular, or at a 90-degree angle. So the normal force is just the support force that a surface pushes with. And here's the key. It always acts perpendicular to that surface. Always.
Okay, to really get a feel for this, think about a trampoline. When you jump on it, you can literally see it sag and stretch to push you back up, right? Well, guess what? A solid table, or the floor you're on, does the exact same thing. It's just happening on a microscopic level you can't see. The atoms in the surface get compressed a tiny bit and they spring back. That springiness is the normal force. Right, so that's pretty straightforward for flat ground. But what happens when the world isn't flat? What happens when we throw an angle into the mix? Let's head to the slopes and find out. Okay, picture a skier on a snowy slope. Now, gravity doesn't care about the slope. It pulls straight down, always towards the center of the earth. But remember our rule for the normal force? It has to be perpendicular to the surface, so it's pushing out from the slope at an angle. And bam, right there. Suddenly, gravity and the normal force are no longer pointing in opposite directions. They're not balanced anymore. And that imbalance is exactly why the skier starts to slide.
So how do we deal with this? We can't just subtract the forces anymore because they're not lined up. We need a better strategy, a smarter way to look at the problem, and the trick is to deconstruct gravity itself. We need to break it into pieces that are actually useful to us.
And here is the absolute game changer for solving these kinds of problems. Instead of our usual boring flat x and y axes, we're going to get clever. We're going to tilt our entire coordinate system. We'll make one axis that runs parallel to the slope, down the hill, and another axis that runs perpendicular to it, straight out of the hill. By doing this one simple thing, the math suddenly becomes so much easier. Okay, so with our new tilted grid, look what happens. That gravity vector, which is still stubbornly pointing straight down, is now at a weird angle to our new axes. So we break it down into two new parts, or components, that line up with our tilted grid. And look, they form a perfect little right triangle. The piece that's perpendicular to the slope, the one pushing into the hill, we find that using cosine. That's the part the normal force cancels out. The other piece, the one that points parallel to the slope, pulling the skier down the hill, that one we find using sine, and that's the one that makes the skier accelerate.
So here it is, all laid out. You've got the perpendicular part, W cos theta, which you can think of as the squishing force that pushes the skier into the slope. That's what's balanced by the normal force. Then you've got the parallel part, W sine theta, which is the sliding force. That's the one that actually makes you go. It's so cool. By doing this, we've taken a complicated, angled problem and split it into two much simpler straight-line problems. All right, quick pop quiz for you. Let's see if you're following along. Look at those formulas. If we make the ski slope steeper, so that angle, theta, gets bigger, what happens to the sliding force? Does the pull downhill get stronger, weaker, or stay the same? Think about it.
And the answer is it increases. You got it. The force pulling you downhill is all about the sine of the angle. And as that angle gets bigger and closer to 90 degrees, the sine value gets bigger too. It's just math. And that's why you feel a way bigger pull and accelerate way faster on a steep, expert-level slope compared to a gentle beginner's hill. Makes perfect sense, right? Okay, so we've pretty much nailed the pushing force of surfaces. So now, let's totally switch gears and look at the opposite, the pulling force that you find in things like ropes, strings, and cables. And this pulling force has a name: tension.
It's a great name, actually. It comes from a Latin word that literally means to stretch, which is exactly what's happening. Tension is the force that travels through something like a rope when you pull it tight, and it always pulls along the direction of the rope itself.
Here's the simplest way to think about it. Have you ever tried to push a rope? It's impossible, right? It just goes limp and bunches up. A rope is only useful when you pull it. That's when it gets taut and creates tension. And a really important rule is that the tension pulls with the exact same force on both ends of the rope.
Now, tension seems pretty simple so far. You hang a 10-pound weight from a rope, you get 10 pounds of tension. Easy. But what if I told you it can get way crazier than that? Let me show you an extreme example that reveals the secret power of tension.
Okay, check this out. We've got a tightrope walker. He weighs about 70 kilograms or 154 pounds. He's standing right in the middle of a wire and his weight makes it sag down, but just a little bit, only 5 degrees from being perfectly flat. So here's my question for you. How much tension do you think is in that wire? Is it his weight? More? Less? This is where the physics gets so cool. See, the wire is pulling mostly sideways, but a tiny little bit of that pull is directed upwards on both sides. And those two tiny upward components have to add up to support the walker's entire weight. Because the angle is so small, the wire has to pull with a massive amount of total tension just to get enough up to do the job. The math for this works out to be the walker's weight divided by twice the sine of that tiny little angle. So let's plug in the numbers. We've got our 70-kilogram walker and that tiny 5-degree angle. And the tension in that wire comes out to, wait for it, an absolutely staggering 3,900 newtons. Yeah, you heard that right. Let's really put that into perspective. The walker's actual weight is only 686 newtons. The tension in the wire is almost 6 times more than he actually weighs. That is just incredible. And it demonstrates a really powerful physics principle. If you have a connector that's pulled almost straight and you apply even a small force perpendicular to it, you can generate an enormous amount of tension. Okay, so let's recap the big ideas from today. Number 1, normal force is that support push you get from a surface, and it's always perpendicular. Number 2, when you're on a slope, the secret is to split gravity's vector into 2 parts, one parallel to the slope and one perpendicular. Number 3, tension is just a pulling force in things like ropes. And finally, the big one, a small force on a taut, nearly straight rope can create a mind-boggling amount of tension. And I'll leave you with one last thing to think about. Next time you see a picture of a giant suspension bridge, like the Golden Gate Bridge, look at how the huge, long cables are holding up the entire roadway. Now that you know the secret of the tightrope walker, can you see how that entire bridge is really just an extreme, supersized version of the exact same physics? It's all about tension.